When looking at what mutations cause the truncated, non-functional mutant proteins seen below, the first step is to use a codon chart to list all the possible codons for both the normal and the mutant strand. The mutation in question is either a deletion or an addition of a single base pair. When looking at a possible deletion, this would result in the codon for the next amino acid starting with a U. Since no codons for the amino acid isoleucine start with a U, it can't be this deletion. The next codon for isoleucine needs to start with an A. So when evaluating an insertion of an A, we see that it is now possible to have a codon for isoleucine because you can have AUU. When looking at the next amino acid in the mutant strand, histidine, the next codon will have to start with a C. This is possible if the codon for the normal strand for phenylalanine is UUC. In the normal strand, threonine can only have a codon that starts with AC. Because of this, the codon in the mutant strand for histidine has to be CAC. The mutant strand is truncated and will need a stop codon next. Since all stop codons start with a U, ACU has to be the codon for threonine in the normal strand. When looking at the codon in the normal strand for lysine, both codons start with AA. This means that the stop codon in the mutant strand will be UAA. When looking at the codons for lysine and glycine for the normal strand, since the mutant strand was truncated by the stop codon, we have no means to determine which codon it could be AAA or AAG. For glycine, it could be GGU, GGC, GGA, or GGG. In review, this is what happens when there is an addition mutation of an A. The final mutant strand reads AUG, UGG, AUU, CAC, UAA.